welcome to talk on Haskell doesn't have to be a hassle. My name's, my handle's ElbinoBunny, and this is my third year at Freaknik, and as far as speaking at conferences go, I have a friend and former coworker who would speak at, he speaks at a lot of conferences all the time. And so he gave me a bit of advice when I said I was kind of interested in looking into speaking at conferences. And he said, I was telling him I was having a hard time preparing all my stuff and getting it ready for the deadline to present. And he said, well, just write the abstract first, and then, before you have anything, and then you'll be pressured to actually get it done. And so I took his advice, and it wasn't, in hindsight, I don't think that's the best idea. That's the best approach. So here's my disclaimer. I bit off more than I could chew. If anyone has read the abstract that was on the Freaknik website, I said I promised an N64 emulator, and I haven't completed it yet. It's in process. I've figured out that it's going to be a whole lot more complex than I expected. I will tell you the method that I was using to build it, and I can show you the code that I've got right now. I've got thousands of lines written, but it's not working yet. I'm using Mupin 64 Plus. It's a GPL N64 emulator. It's written in C. It uses STL for its graphics and inputs, and it really is a good one to do a conversion. And really, what I want to do is I want to show here's C, here's Haskell, kind of a Rosetta Stone of what it would look like between the two. I think I'll probably have that done in a few months. I ran into snags because right after I submitted my abstract, I lost my job, and then my wife lost her job about a few weeks later. And so I was, things were really, really stressful, and I was doing a whole lot of things other than this talk while that was going on. But now my wife's got a new job, and she's making more money, and I'm the stay-at-home dad for our son. So I'm going to be spending a whole lot more time on this. And my functional programming meetup group in Knoxville is hounding me to get it done. So I should be getting it done pretty soon. Okay, so who here has used Haskell at any point? Okay, a few people. When you've used Haskell, has it been, you've kind of dabbled in it, or would you consider yourself a dabble?
It was in
Hello world.
messing with the show.
Right. Well, and that's, I've been using Haskell, kind of forcing myself to try to learn Haskell for about 6 months now. I'd like to consider myself an intermediate developer with it, but it has been quite the challenge to learn. But I guess what everyone may raise their hand knows is Haskell's a pure functional programming language. It's fully static, strongly typed. And it was, you may not know, that it was sponsored and developed by a team of super smart people at University of Glasgow in Scotland. And it kind of gets a reputation for being an ivory tower, very academia language. I sometimes, it kind of makes me chuckle inside to think of a whole bunch of Scottish professors sitting around drinking scotch and saying, you know what we need, you know, would it be possible, maybe we could build a programming language where we write programs that don't have any bugs once they're compiled. And then they all laugh, but then one guy says, wait a minute, hold my scotch. And that's kind of how I see Haskell. So they created the Glasgow Haskell compiler that came out of the University of Glasgow. And it is the most popular Haskell compiler. And that's what I'm using in all my examples here. I went over that it's got a reputation of being a programming language really only for mathematicians and theoretical computer scientists. But in practice, I have found Haskell to really be essentially C without pointers when you really get down to it. Now, why would I use Haskell? Well, so, you know, before I lost my job, I was writing code full-time, C#, and then I would come home and I'd want to write more code. I want to get things, you know, written out and done. And I was having to debug it. You know, I would find something would go wrong, and at the end of my hard work day, I didn't want to debug more code. You know, it was, it was exhausting. So I liked the idea of having to only write something once. And Haskell, the full problem domain has to be known in order for it to compile, for the most part, if you're talking pure functions. There hasn't been a whole lot of syntax that's changed over the years. It's very stable. Pure functions in the language can be automatically asynchronously parallelized by the compiler in certain cases. And you can just put a slash thread or a dash threaded option on the compiler, and you can run it across multiple cores. And certain pieces of your program will just get picked up and distributed. It can operate as a lower level language, and it compiles all the code down to a system binary. It ties in easily with C, so if you have you have C DLLs, or you want to have a Haskell DLL that you import into C, they go both ways. The same Haskell compiler runs on x86, x64, and ARM architectures in Linux. Now, Haskell actually is a hassle, and in the sense that because a lot of people use it theoretically, a lot of the documentation I've found is, from mathematician and theoretical computer science people. They really don't understand why you would be using it to do anything, constructive, like building an N64 emulator. Those who do understand it, these people seem to have a different language than other developers. They've made up all their own terms, and I've had to basically build my own lexicon out of when they say wire, it means event handler. When they say, they have certain terms for each thing, and I'll go into that further. There's a stigma that Haskell is, really just an ivory tower language. And I've run into this in a lot of my functional programming meetups, is I'll start trying to talk Haskell with people, and they go, I'll talk about React, I'll talk about JavaScript, I'll talk about F#, but I don't want to talk about Haskell because it's too up here. And I think there's a misconception about it. There's, not as much developer support. Certainly, there is a Haskell IDE that works pretty well. But in general, you're not going to get IntelliSense, you're not going to get anything that really just writes your code for you that I've seen. Truth be told, it's actually kind of a challenge to learn. That's kind of, it's not, it's a hassle when I'm mentally fatigued, but in general, I really like a challenge. And so Haskell really, has been, fun to get into. Other benefits to Haskell, code can be extremely concise. There's no real need for boilerplate code. You just write a function that you don't have to repeat yourself anywhere. Lots of shortcuts that can elegantly do most anything. There are extensive libraries that support advanced concurrent programming. So you can really take if you've got a multi-core system, you can really leverage all that bandwidth. Haskell also holds no punches. If you want to learn pure functional programming, Haskell's your language. It forces you to think functionally. Whereas programming languages like F#, it says it's functional, but you can still do a lot of object-oriented programming and structured programming. Whereas Haskell, it's got to be functional. Okay, getting into the syntax. Important data structures to know, most important. You have your list and your tuple. List is probably, most everyone in here probably knows. List is list of items that have the same type. Tuple is a container of items that can have multiple different types. So your tuple is going to be your object, your list, or more your arrays. You can use the type keyword to define any type you want to, and you've got primitive types available, int, float, character, etc. String is available. It's actually a list of characters. So creating a new type is pretty simple. You just have the keyword type and what you want to name the type, and then you set up what it equates to. This is the same as type def in C, essentially. And then you can have what I like to call properties, but these are really just functions. We have a function that has a pattern matching, and okay. Let me actually go into what you're seeing here. So this top line for position X, so we're defining a pixel position. So we have X and Y, and so in our definition of a pixel position, it's going to be a tuple that has an integer and an integer. And so that's your X and your Y. And so these functions will pull back position X or position Y. And so that way, and then we can define out, strongly typed, say we're going to receive, for position X, we're going to receive pixel position, and we're going to return an integer. And so right there where we have X and then the underscore, X is when we receive pixel position, X is what's going to be returned, which is the first integer in pixel position. So then we can also say, once we've defined pixel position, that we have a rectangle. And we could define a rectangle as either a list of pixel positions, in which case we'd want to stop at 4 items in the pixel in the rectangle, or we could have a tuple of 4 pixel positions, and then that could be a rectangle. 2 different approaches you could use. Important to note, case matters in Haskell. You will have all kinds of compiler errors that are difficult to understand. If and this happened to me, if I screwed up the casing, I didn't know where I was at. So once I figured out the case mattered, items that start with an uppercase letter are treated as types or modules. Items that start with a lowercase letter are treated as functions and values. Right here, we're pulling the nth item from a list. So you can pull out a 2, or the index of 2 will return C in this case. Concatenating lists, very simple. But I want to get into, who here knows what a higher order function is? Okay, very good. A higher order function, and this is a computer science definition, is a function that can take a function as an argument and or may return a function as a result. So when you have defined out a function, you can pass in another function to that function. And then you can return as the result a function. Haskell has this, it's an integral part of the language. There are other languages that are implementing it now. If you think of lambda expressions, you probably used it and not realized it if you've used lambda expressions. But integral to Haskell is higher order functions. Pure functions, definition of a pure function. A pure function will always return the same result given the same arguments. And the process by which the function is executed does not cause an observable side effect. So what this means is that everything that happens inside the function, so the function, when the function runs, it does not change anything outside the function. It does not touch anything outside the function. It pulls in its inputs, its arguments. It uses that. It does its thing, and then it returns out. When you have a pure function like this, you can dependably know that it's going to do exactly what you think it is for the same input every time. It's consistent. And this is really the building block of Haskell and why it's so reliable. All values in Haskell are immutable, as they cannot be changed once they're created. So if you say x equals 5, x will equal 5 forever. You can't then go say x equals 6 or x plus plus. That doesn't work in Haskell. Because of this, there is no while for each, any loops. Loops are achieved through recursion. So, for instance, we have a map function that mimics a for each loop. It takes a function, whatever you want to run. So you have a function, the thing you want to iterate through, and you have a list of parameters. And it returns that list of parameters after it's been taken the function, and the function has been applied to every single item on that list. Zip function illustrates this as well. You take two lists of any type, same size, and it zips them together and makes a tuple, a list of tuples that contain both lists, the items of both lists. So in this case, we have current list 0, 1, 2, 3 in strings, and we take the length of the current list, and we have an enumeration. Oh, I didn't. I actually meant to fix that. So it should yield 0, 1, 2, 3 in the comment here. I meant to fix that last time. But yeah, if it actually ran, this would be 0, 1, 2, 3 going across. And so you can have a key value pair object that you can pass around. okay, so we know what pure functions are, but how do we impure? Because at some point, we're going to have to do something important. If you had only pure functions, then you couldn't talk to the I/O. You couldn't use a random number generator. You couldn't do anything that you'd really need to do in your program. So, of course, our objective as Haskell code developers is to place as much code as possible into the pure functions, because that actually reduces the potential for unexpected program behavior. We always know what the result of a pure function is going to be. And they can be asynchronously parallelized very, very simply. It eliminates bugs when we use them. But when we actually want to do something risky, we have to use what's called a monad. So to actually run a Haskell program, we, like many programming languages, you have a main method. And the main method returns an I/O, empty tuple, which really, in this case, we can think of this as a void, if it were C. It's returning void. In which case, it's also returning anything you want it to return. I/O, in this case, is of type monad. It's the I/O monad. In main, we have main equals do. And we can put any number of instructions under that do statement. And what that does is it will actually run each instruction incrementally without certain flags or intervention. This is not easily asynchronously parallelized because it's supposed to be iterative. It's supposed to be run one after another. And each one of these lines is going to return an I/O monad type. So this is hello world, by the way. And if you do that, what it's going to do is it's going to print out hello world to the screen and then return back I/O, the I/O monad. Okay, so if we've got that main method, we say, okay, I want to use a function, and I want to return a value and store it. When you're pulling a value from a function that returns a monad type, you'll have to use this arrow-looking operator, and you can just, okay, I'm going to, you just write the value or the name of the value that you want to store it in, and you just call the function and you'll get back the result. But when you want to pull a value from a pure non-monad, non-suspect function, you use the let keyword. And so you say let the variable name, and then you call the function that way. So, first example, I have a menu display program. Okay, so right here, what we're going to do is, that could be bigger. Get it. So we have our main method, and it's basically just going to give us a menu. And right here we have condition, and we're going to say, okay, if the input is H, then print hello world. If it's Q, exit. If it's anything else, show the menu again. And if you notice here, we're calling main again. In other programming languages, this would be bad practice, but in Haskell, this is normal. So we're going to run that and see what happens. So you just compile it like this, GHC main. Oops, we have a problem. Right here in the condition, we have 3 items, 3 lines here. Put string line, we have the 2 of those, and then we're calling main again. Now what is happening there is we have several types that are being that are pulling back, and the compiler is saying you can't do that. You can only when you go off and you execute these things, I should only be receiving back an IO monad. And so in which case, if you'll notice, we can't have 3 different items executed underneath the if statement. We should only have 1. And so what you can do is you have to put into a function. Up here, we have our hello world function. It has all those things that are going to execute, but it's only going to return the IO monad. So, have down here, hello world function. Compile it, looks good. And now we've got our program. So, we press H, we get hello world, press Q, and we can quit. Another thing we can do is we have this, I built out this method here, and we have guards. And what guards do is they act as kind of a switch statement. So in all of your functions, you can put these types here that act as, it's basically a condition. We have conditions all the way down. And then when we have this where statement here, we can actually define out other variables that we need to use in our conditions in order to do any calculations that we need. So, or any manipulations. So here I've had it to parse out the input, and it'll do it exactly like it was doing before, and then it will tell us what type of letter, what case was chosen. So in this case, we don't even need any of these conditions anymore. We can just comment them out. And we can just do parsing. And so now it does hello world, letter chosen was H, was lowercase h. With uppercase H or the uppercase H. Okay. So I like to think of my Haskell programs as Kanban boards. Does anyone know does people know what Kanban boards are? So basically, a Kanban board, you have in a lot of software development shops, you have like a wall of columns, and each column is a step in a task on in the life software life cycle on its way to being fully developed and shipped. I like to think of each column as a function, and my sticky note is the type that's moving through all the functions. So in this case, for the main method, we have an object of type IOMonad. That's the sticky note, and it's moving through all the instructions all the way down to the do statement. It goes through that chain of functions, and it can go back through functions. It can be a recursion. It can loop through. Multiple steps is needed, and there can be control flow. For my N64 emulator, I'm sending an object of type device through all the functions per each instruction that's pulled from object of type gamewell. Okay, so how do I do neat, tricky stuff though in Haskell? Here's an example. I want to pull in arguments from the console terminal, and I want to use them. So here we're getting system.environment. All we have to do for this really is to using the monad assignment one operator. We're going to get all the arguments, and then I'm going to print them out one at a time on the screen, so that they can be seen in the console. And once they're pulled in, you can do anything with them with this kind of example. But we're just going to print them out to the screen. And as I said earlier, you can use the map pure function in order to do a for each on pure variables. In order to do this for the monad, you need the map m function, because we're doing it on a monad. It's not going to be returning A, it's going to be returning monad A. And then if you want to ignore the output, you put an underscore after that. It's one of those things that took me a lot of Googling to figure out how to get certain things to work. So let's run this and see how it works. Okay, so there were no arguments, so there's no output. So now we have arguments 0, 1, 2, and 3. And you can pull in any of the arguments, and you can use them in a practical program. Another thing that I wanted to demonstrate is how to do random number generation. So I built a character generator for role-playing games. And here I put several different modules in place. So this is how you can get a random number in Haskell. There's a system.random library, and it uses the using the IO monad, we can pull back an integer. And this is basically rolling the dice. So this will, based on the numbers that go in, if I say pass in a 0 and an 18, it's going to give me an integer between 0 and 18. And so here I've got different vocations for my character: bard, cleric, demonologist, hacker, healer, you name it. We can get one of those vocations by its index, and this returns the max number of vocations. Now this is a module. You can make modules, put them in your program directory, and module is basically, like it is in a lot of languages, when you put the name of the method or the value up here, the function or the value up here, then it determines whether it's public. So if you put it in there, it's public. Everywhere else, it's private. So then, this is the main method. It'll generate a character with, all the stats with the dice rolls. And there we go. So we got an elf that's lawful good, happens to be a communist, and he's a pretty good demonologist. He's not very lucky, but he's got a pretty decent amount of charisma. Okay, so what about event handling in STL? So like I said earlier, the Mupin 64 plus emulator that I'm trying to mimic in Haskell is written in C, uses STL libraries, and it handles graphic and game input using STL. Event handling is done in C. They have their own event handler that they've set up. Event handling in Haskell, from my research, seems to be best achieved using what are called wires in the netwire package. If you're using Haskell, say Ubuntu, like I am, you can just look for that netwire package using Synaptic Package Manager. You can install it, the dev version, and it will be available in any of your Haskell programs when you go to compile it in GHC. One thing you want to do when you work on netwire stuff is brush up on arrow syntax. Google for arrow syntax and read up on it. It will help you figure out what is going on. Otherwise, you'll be lost. I'm still a little lost on how it all works. I'm going to show an example program that I found online, and it's at this website. I did not come up with this code, and in fact, I'm trying to work through it to figure out how to use it and pull it into what I'm doing. But it gives a good demonstration of how to draw a rectangle and build events such that you can press the left and right keys to move the rectangle back and forth across the screen, thinking like Pong or breakout. Okay, so we are importing the wire, the arrow syntax, and the monad to control those things. We're importing the STL library and the event handling library for the wires. Defining out movement in the game event. And then these functions set up the wires. Set up our surface. Polling events. Combine all the events. And then handle positions. Handle output. And then here's our main method. Okay, let me demonstrate. We have a rectangle. So if you're interested in STL, I'd recommend going to that site for further reading. I guess further things that I'm going to be doing is looking into parallel concurrent programming in Haskell by Simon Marlowe. He is one of the people who developed, who actually actively develops the Glasgow Haskell compiler in Scotland. And so I'm going to be picking up that book and reading through it. And I wanted to put that on the reading list. Learn You a Haskell for Great Good is where I started to learn Haskell. It's an incredibly good resource. It's free. It's on that site, learnyouahaskell.com. I read it a chapter at a time and just did everything in the chapter. If I didn't understand something, I just kept reading. That's a very important thing to do with Haskell. Don't sit there and just chew on it. Just keep going. Haskell.org has a whole ton of good resources listed out. Hoogle is on Haskell.org, so Haskell.org/Hoogle is a Haskell reference search engine. So anything, compiler blows up and says, something crazy and you don't really know what it's telling you, type it into Hoogle, and it's very easy to get an answer. For those who are interested in the movement demo that I showed, there's also another resource that I found called Getting Started with NetWire and STL. It explains a lot of what's in the minimum game logic tutorial and how it works. His code examples don't compile. They don't all compile fully correctly. But his explanation of how it all works is pretty good. So I guess that's about all I've got. Thanks for coming. Does anyone have any questions? Okay. Thank you.